How's it going, everyone? Welcome to the 10th drill. Today we're going to be talking about multiple regression and all the information that's in the outputs from your multiple regression. I've already loaded the tidyverse and LM support libraries. If you don't already have the car package, you will need to install it today. There's a lot of things that we ultimately use for, or that a lot of people use from the car package, but there's one thing in particular today that we'll use it for. We're going to start by reading in the data here, and this is the data that Bill has been talking about in lectures with the number of times that people go to see a doctor. Since this is the first time that we worked with it here in drill, I went ahead and included like a data dictionary for this. So we have this X1, just ignore that. It is just kind of an extra column that got put in there. The time DRS here, time doctors, that's the number of times that they went to the doctor or mental health professionals. PSYC and MinHeal will be physical health symptoms and mental health symptoms, the number of symptoms that they have. Stress is just a measure of stress that reflects both the number and importance of changes in life situations. So it's a computation that goes based on not just like how much stress are you feeling 1 to 7, but also a function of how many stressful things are in your life and just how stressful are those things. So that's where that number comes from. This esteem is their self-esteem, and higher number, it means more self-esteem. Control is their locus of control and their beliefs that there's an internal versus external locus of control, and higher numbers indicate that they have a more internal locus of control. And then age is in 5-year bins. So when we look at the descriptives of these things, we can see, for instance, with the time doctors, we have an average of 7.63 doctor's visits with a standard deviation of 10.10. The fact that your standard deviation is bigger than your mean tells you that there's a lot of variability in there. Physical health symptoms, like on average, there's about 5. Mental health symptoms, on average, is about 6. Et cetera, et cetera. We're not going to spend a lot of time here. I'll let you explore that more on your own. What we do need to do is we're going to mean center the 3 predictors that we're going to work with today, which are the physical health symptoms, self-esteem, and control. So making PSYC C, esteem C, and control C, just by subtracting the mean from each of those 3 things. And so now if I look at my glimpse again, then I can see I now have those 3 centered variables in my data set. So let's start by looking at a simple regression, just that 2-parameter model, and to see here, what I want to point out is that as far as the terminology used, you could read this as Model 1 is time doctors regressed on physical health symptoms, or mean-centered physical health symptoms. So Y regressed on X. You could say time doctors predicted by physical health symptoms. Time doctors as a function of physical health symptoms. So as far as this tilde here, the main thing that I want to drive across is it's Y regressed on X. Your outcome regressed on your predictor, not the other way around. So just to keep that terminology straight, just remember that you read this as time doctors regressed on mean-centered physical health symptoms, not your predictor regressed on your outcome. So I also have this note here that this is the last time that I'm going to include this 1+ part, that intercept, explicitly in there. Again, we've mentioned before that if you leave off the intercept here and just have just y regressed on x without that intercept plus x, it will automatically put that 1 in for you. But I just want to make it clear that this is why it's a 2-parameter model. You have a slope for physical health symptoms, mean centered, and you have the intercepts, which are your 2 parameters. If you just saw it this way, some people might be like, oh, well, there's just this is a 1 parameter because it's only regressed on one thing. Well, no, it's actually regressed on 2 things because that intercept is just put in there implicitly. But I normally don't include the 1 in the model like this, and so from now on I won't. And I just wanted to make this clear one last time that that's how this is working. So let's take a look at our model summary then, and talk about what all of these different things actually mean. So here, well, first of all, apologies, I actually had already ran. As a reminder, if you just ran this line, yours won't look like this. It's going to give you scientific notation. And so that's to turn that off. You'll tell it you'll run options and SciPen equals something. In my case, I ran SciPen equals 20, which tells it that it needs to be something that is times 10 to the 20th before it goes to scientific notation. And so that's why throughout this, my p-values and all those different values, I won't see scientific notation, but you will if you haven't run that options SciPen command. But anyway, so as we look through our output here for our model summary, let's go over just piece by piece what all information is in this model or in this output. So first we have our intercept, and I've been telling you for a long time that the intercept is the mean outcome when all your predictors are 0. Well, since the mean of physical health symptoms is now 0 because we mean centered it, that means that this estimate, your intercept, is the average number of doctor's visits for somebody with the average number of physical health symptoms. So it's not for somebody who has 0 physical health symptoms, because we have mean centered it. That this is we would expect somebody with the average number of physical health symptoms to visit the doctor 7.6 times per year. And then so we also have our standard errors of those estimates. Same thing here, that this is the standard error of that slope. Not going to get into its computation. Don't need to. You just need to know what that is. And then we also have our F and P, or T if you don't have this T equals false. Then this will report T instead of F. But as a reminder, what this F test versus this F test. So just to be clear, there are 2 separate F tests in this output. One here, one here. And each one of those tests a model that includes all the parameters in the model as your augmented model against a compact model that takes out that one focal parameter. So in other words, if you take out this intercept parameter, and then compare a model that just has phi heel c in it versus one that has the intercept and phi heel c, then that F that you'll get when you do that comparison is going to be 320.5. P is less than 0.001. And this one is if you do a model that has an augmented model that has both the intercept and phi heel c, it has all of the parameters in the model. In this case, that's only 2, is your augmented model. And then if you take out this focal parameter, if you take out phi heel c and make a compact model that has just the intercept, then that's where this F and P come from. So again, these f-tests or t-tests, depending on how you have it, simply test a model that takes out that focal parameter on that particular line. And what that means will make a little bit more sense here in just a little bit once we have more than one slope line. Beneath this down here at the bottom of this output, it also gives us our sum of squared errors and degrees of freedom for the compact model. And it says r squared is 0.2103. This r squared, you might hear called like just r squared. You may hear it called the model r squared or overall r squared, or the multiple r squared. In this case, why it's called the multiple r squared doesn't really make sense because there's only one thing in there, but that's what this r squared is. It is the overall like model r squared. If we run, instead of running model summary, the LM support function, which is my preference, if you just run the base R summary function on that same model, it gives you largely the same information, except it also gives you this stuff about the residuals that I don't need. And then down here, it also gives you this additional line of an F statistic. What this is, you may hear this called an omnibus test. And what this F statistic does is it simply compares the full model, that augmented model, a model that has everything in it, against an intercept-only model. Here you notice that if we go back and look at the model summary, so that we can report it as an F instead, you'll notice that the F statistic here of just the summary function matches this F statistic in our coefficients table when we actually report it as an F, because my point is that the base R summary only reports this test as a T and it doesn't report it as an F. But if you square this 10.86, you get that 117.9 that is that F or this F right here. So in other words, you notice that the model F statistic, that omnibus test, matches this exact test, and that's the case when there's only two parameters, because again, what this omnibus F test actually tests is a model with everything against a model that only includes the intercept. Well, this test here, or if we put it in F, this test here tests a model that has everything in it, which is only those two parameters, against a model that takes out that one parameter, which happens to mean that its compact model that it's testing it against is the intercept-only model, which is why when you only have a two-parameter model, the overall model F here is the same as what's in that coefficient table here. You notice that it also, when you run the base R summary, that also gives us, we'll run that again, that also gives us down here this residual standard error. And so the computation for residual standard error is pretty simple and straightforward. If we run that, we can see how that number is computed. And then finally, like it also has this adjusted R squared. And so as far as where that adjusted R squared comes from, first let's remind ourselves what the adjusted R squared is for, and that is that we make an adjustment to our R squared because anytime you put more predictors into the model, at worst your model will not get worse. It cannot decrease R squared if you put in more parameters. Chances are that it is going to decrease R squared with any parameters that you put in at all. It may not decrease very much, but it's going to decrease, and so you can't just think about this R squared in terms of overall, that because, well, if you just keep adding parameters, your R-squared is going to keep going down, but you can't just say like, oh, well, we're explaining more variance, so that's good. This adjusted R-squared makes an adjustment based on the number of parameters that you include. And so if we look at the last drill 9 script, where I copied out and I just said that there's this unbiased estimate of eta squared or r squared, and I created this function. And now if I just run that function based on the PRE that we got, the n for this sample, and our degrees of freedom here, we see that that unbiased eta squared is what that adjusted r squared is. So in other words, this adjusted r squared is just making an adjustment to that r squared that's based on, it kind of penalizes your r squared a little bit as you include more parameters, so that the juice has to be worth the squeeze, and you're not just throwing in parameters that aren't actually helping your predictions in a meaningful way. You would do well to yourself to remind yourself, and Bill kind of touched on this, especially on Wednesday, that I understand that it might seem frustrating as early young statisticians that there are all these names for the same things, and I agree that it is kind of frustrating. And so that's why I say that you should really remind yourself that PRE, eta squared, r squared, like these are all just different terms for the same ideas. It's some way of putting a number on, the amount that error was reduced. It's the proportion of the reduction of error. And personally, anecdotally at least, oftentimes what I've noticed is researchers who like to talk about ANOVAs and ANCOVAs and such, they tend to talk about eta squared as their effect size, and the researchers who like to talk about linear modeling tend to prefer talking about r squared, but again, they're interchangeable. Also, SPSS outputs eta squared and partial eta squared as its default thing, which I think is really what's driving most of that one being used. And that also applies to, I'll speak more to why like SPSS defaults like guiding, kind of driving how we report things. Also, here in a bit, once we talk about the model r squared on, the model f test on the multiple regression down below. But yeah, so in short, this when you look at this adjusted r squared, that is just that the unbiased estimate of eta squared or PRE that we talked about last week, and that's reported as adjusted r squared if you use base R's summary versus LM Support's model summary. So if we want to check our effect sizes, we can just use the model effect sizes, and it's going to give us that our delta r squared, change of r squared, is 0.2103 for physical health symptoms. And oh, sorry, I just realized, my apologies, we never actually, let me take a step back to go back and talk about this interpretation, because I didn't speak to this particular number, which is, so we know that we expect 7.6 doctor's visits for somebody who has the average number of physical health symptoms. This number, again, just represents how much we expect that to change with a 1 unit increase in physical health symptoms. So in other words, somebody who has the average number of physical health symptoms, we're predicting 7.62 doctor's visits per year. Somebody who has 1 more physical health symptom than average, we expect that to be 7.62 plus our slope, which was 1.97. So we expect some 9.59 doctor's visits for somebody who has 1 more than average. If somebody has 2 more physical health symptoms than average, we would predict them to visit the doctor 11.56 times per year. So for each 1 unit increase above the average of physical health symptoms, we expect 1.97 additional doctor's visits. So sorry that I kind of went out of order there, but anyway, so we have our model effect sizes will give us the effect sizes, and then if you prefer things in the ANOVA framework and like just in your field or subfield, ANOVA tables are what's more reported, and so that's what you're more comfortable with. Well, you can just throw that model into ANOVA and it will report the same thing. It gives you that same F value and the same P value. But it's just another way of looking at the same thing. So let's say that we add 2 more predictors now to this model. So we're going to take our model, which was just number of doctor's visits regressed on the number of physical health symptoms, or the mean-centered number of physical health symptoms, and we're going to add self-esteem and locus of control. And both of these also being mean-centered. So we could create the model as you might expect, just by saying, number of doctor's visits regressed on centered physical health symptoms plus centered self-esteem plus centered control. There's also a function called update. And what update does is you put in, some model, and then you tell it how you want to update that model. And here is the formula. It's period tilde period plus esteem plus control. This period tilde period, what that says is like, okay, if we look at what that model is, this model that we're updating is this. So this period here says everything on the left-hand side of the tilde in the model. So if we find the tilde, everything on the left-hand side, include that. Leave it how it is. Like, put that period in. Then over here, where we have a period, that's saying everything on the right-hand side of the tilde. Leave that also as it is. But then also add esteem and control on that right-hand side of the tilde. Here, just as an example of how it would be different, if we just run this portion right here, we could see that what it's actually doing is taking that model, and you can see that instead of having period tilde period, I put control C on the left-hand side of that tilde, and so that's what it did. It changed my outcome to control C, and it added esteem to the right-hand side, where the period says to leave the right-hand side as is, but then also add esteem to it. And here, if I leave the left-hand side the same and then change the right-hand side to just esteem C, and I run that portion, you can see that it took out what was in Model 1 on the right-hand side and instead put this one thing in its place. So that's how this update function is working. But these 2 lines right here are 2 ways of doing the same thing. So either one of those things work. So now let's take a look at this model summary and see what we have here. So on this model summary, we have the same stuff as before. This is our prediction for how many doctor's visits there are when everything else in the model is 0. And again, this is why I put this has been at the top of several scripts. The intercept is the mean of the outcome when all the other predictors are 0. So in this case, that means that we expect 7.62 doctor's visits for someone whose centered physical health is 0, whose esteem is 0, and their control is 0. Well, what does 0 mean? Because these are the centered versions, mean-centered versions specifically, that means that 0 is the average. So this is the number of doctor's visits that we predict for someone who has the average number of physical health symptoms, the average self-esteem, and the average locus of control ideology. let's talk about, before we get into interpreting these partial slopes and why it's called a partial slope now, since we're doing multiple regression, let's talk about these f-tests and what is being compared with each of these f-tests, where we see that these two f's are not significant and these two are. So what is being tested here that is significant and here that is not? So as a reminder, and this is where I think it makes a little more sense now that we have multiple predictors in there to talk about some of these things. So here, with this first line, just this one right here, so all we're focusing on is this f equals 319.426, p is less than 0.001. When we look at this f-test, what it is comparing is the full or augmented model. Across all of these, the full or augmented model is going to be a model that includes 4 parameters. It has the intercept and a slope for physical health symptoms, esteem, and control. So 4 parameters in each of these models. And our augmented model is always going to be that full model. What changes between each of these f-tests is what is the compact model that it's being compared against. So in this case, where we get on the intercept and we get an f of 319, that means that if we make the intercept our focal parameter, and so if we compare an augmented model that has everything against a compact model that removes that focal parameter, in other words, if we take out that intercept, so here all I have is it's the same model, that it has the 3 slopes of those 3 variables, but I put it in a 0 here to explicitly tell R, do not include the intercept, remove the intercept. And if we run that, we can see that that is the exact same f value and the same p value that we get for that intercept. So then here, this 117, what is it comparing? Well, that is comparing a augmented model that has all 4 of these parameters against a compact model that removes this focal parameter. It removes physical health symptoms. So you can see here now in the compact model, I'm simply regressing the number of doctor's visits on esteem and control and taking out those physical health symptoms. And again, here the intercept is in both of these. So basically we're comparing this 4 parameter model against a 3 parameter model, that the 3 parameter model specifically takes out that physical health symptoms. And when we run that, we can see that that's where we get our f of 117. For this next one, for f of 0.066, all we're doing is we're comparing an augmented model that has all 4 of these parameters against a compact model that removes this one focal parameter. So if we take out esteem, which is what we've done here in the compact model, if we take out esteem and run that, we can see that, again, our f lines up with that f that we get, and that's where this p-value is coming from. And then finally, if we look at this one, where do we get this f of 3.13? Well, if we compare an augmented model that has all 4 of these parameters against a compact model that removes this focal parameter of control C, so now we have phi, heal, and esteem, but not control in the compact model, but we do include control in that augmented model, we now get that f of 0.313 and p of 0.576. So now that we're talking about multiple regression, let's go back and talk about this that omnibus test that we talked about. So if we, again, you have to use the base R summary, not model summary, to get it, because LM supports model summary, does not report this F statistic, the omnibus overall model. And the reason is that that's usually unimportant and uninteresting. But why is that unimportant and uninteresting? Because recall, we said, like, this F statistic, that omnibus test, simply tests a model that has all the predictors against an intercept only model. When we ran this on the first model, that it was the same because there was only the one additional parameter. So the compact model is an intercept only model. Now that we have multiple regression, though, you'll notice that this F statistic does not match up with any of these, because it's no longer testing the same thing as a 2 parameters model here. So this simply says, if we take an intercept only model as our compact model, and then the augmented model that has all 4 parameters in it, and compare those, that's where we're getting this F statistic of 39.36 on 3 and 441 degrees of freedom. P is less than 0.001. So in other words, all that this omnibus test tells us is, like, well, including the slope of physical health symptoms, self-esteem, and control does reduce error significantly beyond just doing a mean only model, an intercept only model, which of course it does. And that's why, like, I hope that makes it clear, like, why that's uninteresting, why this is pointless and doesn't really give us anything useful to say, like, well, of course, if you include the predictors that we presume are related to all of these things, like, that should reduce error more than just predicting the mean for everything. And so, yeah, usually, that model F is significant, and whether or not it is, it doesn't really matter, because it's not, it's just not a meaningful comparison. And so, what we really want to know here, and I really should have spell checked all this, I suppose. Sorry about that. So since this is pointless, like, I don't report my model F's, and if I had somebody that asked me to report the model F, I would simply explain to them, like, well, sure, I'll give you the overall, that omnibus F, but that doesn't really tell you anything meaningful. All that tells us is that including predictors significantly reduces errors beyond not including predictors, and that's just not interesting to me. So since that's, like, pointless, what would be something that would be meaningful is, like, perhaps comparing our 4-parameter model to that 2-parameter model, the first model that we did. And in other words, what we're asking here is it worth it? Is the juice worth the squeeze to include these 2 additional parameters? So when we initially just had these first 2 lines, like here, the esteem and control are not significant. These do not have a significant impact on our predictions. But we want to know, nonetheless, does including them reduce error significantly beyond leaving them out? And we'll come back to that, because I'm sorry, again, I realize I just didn't talk about these partial slopes. So let's get back to that for just a second. Let's talk about what it means to have a partial slope here. So again, this intercept, we expect 7.62 doctor's visits for somebody with average physical health symptoms, esteem, and control. The reason these are called partial slopes is basically essentially what I just now said. Notice how I didn't say, like, this is the average number of doctor's visits, because it's not necessarily. It is conditional on, this is the average number of doctor's visits for somebody with average physical health symptoms, average esteem, and average control. This 1.98 suggests that for each 1 unit increase in physical health symptoms, we expect that average, that estimate, to go up by 1.98, controlling for esteem and locus of control. because we can't just say that we predict that there's going to be a 1.98 unit increase, for each unit of physical health symptoms, because it might be different for somebody who has, higher esteem or lower control than average. But we don't have that information in our model. We don't know. We can only say, after we control for these other variables, here is what a 1 unit increase in X, Y, or Z does. So here, controlling for, holding constant the average control and average physical health symptoms, for each 1 point that esteem goes up, we expect 0.029 less doctor's visits per year, but that's not even a significant effect. Like, that slope is not significant. And then same thing here, for holding constant or controlling for average physical health symptoms and average self-esteem, for each 1 point increase in locus of control, we expect that the number of doctor's visits to go down by 0.2, essentially. So the reason these are partial slopes, again, is because you cannot talk about them in isolation. You cannot simply say that this is a 1 unit increase in control is predicted to decrease doctor's visits by 0.2. That is incomplete. You have to finish that sentence by saying controlling for physical health symptoms and esteem, because information about both of these things are included in that slope. But specifically, the only thing that is included in this slope is the mean of physical health symptoms and the mean of self-esteem. So that slope only speaks to the predicted change based on a 1 unit increase of control at the mean of esteem and the mean of physical health symptoms. So I hope that makes it clear, at least clearer, why we say that when you're doing multiple regression here, that these are partial slopes. That it's partial because it is conditional on these other values at a specific point, and it doesn't just apply unilaterally. You need to say that this is this is the slope of physical health symptoms controlling for esteem and locus of control, or holding constant esteem and locus of control. In this case, we're holding it constant at their means, but that's what this means, that we expect this number to go up by 1.98 for each 1 unit increase of physical health symptoms if we keep esteem and locus of control held constant at its mean, which is what we mean by controlling for esteem and control. So again, sorry that I'm kind of jumping around out of order here, but now let's get back down here, where since we know that this omnibus test here is pointless and it doesn't give me anything interesting to say, yeah, using all 3 of these predictors reduces error more than just using the intercept. Big whoop. So instead, like I said, let's see, well, our original model, if we compare our first model and our second model here, we just had this one, 2 parameters, the one slope plus the intercept. So our second model, we're doing a 4-parameter model, and do we really want to do that 4-parameter model? Is it worth it? Can we statistically justify using a 4-parameter model, even though if we just look at our R squared, we can see that R squared goes up. It was in the original model, our R squared was, the multiple R squared was 0.2103, and now that multiple R squared is 0.2112. So R squared went up. We explain more variance by including these 2 extra parameters in here. So that's good, right? Well, not necessarily. We don't know. We have to do these model comparisons to find out, are those additional parameters that we included worth it? Do we significantly reduce enough error to justify including those additional parameters in the model? And so to do that, we can do a model comparison, and we will just use our compact model will be that 2-parameter model that has the intercept and the slope of physical health symptoms. So this is our compact model. And then this is our augmented model. So we're going to compare a 4-parameter model against a 2-parameter model. And when we do that, we see that we just look at that sum of squared errors for each of those two models. And our delta R squared tells us how much R squared changed. So yeah, R squared went up by 0.00096. But is R squared going up? Is that reduction of error, by this much? Is that worth having 2 additional parameters in the model? And the answer is no, not really. P is 0.76. That's not a significant reduction in error. So in this case, you wouldn't want to include these 2 additional parameters. So this is one way that you can look at, you can compare nested models, for instance. And so one thing that I've done is where I have, if you want to say like, okay, well, do we want to include this additional predictor in the model or not? We'll do a model comparison with and without that predictor or those predictors, and you can find out whether or not statistically that juice is worth the squeeze. If you're using, you could use the ANOVA function as well. And like I said, that now that's just, some people are more comfortable in ANOVA world. I don't. I always only speak in terms of the general linear model and don't put, case-specific names like ANOVA and t-test and such on it. But this gives you the same information, just in, a slightly different way. As far as did we cover everything? I would also like to real quickly mention that here now maybe it might make sense, because I didn't put in the model effect sizes. Sorry guys and gals and whatever else anyone might identify with. We're going to put in my model effect sizes here, and let's look at our model effect sizes of model 2. And so when we look at our summary, and it gives us that multiple R squared of 21.2112, what that is looking at is with all of these different things, if you add up all of the delta R squares, what is the total R squared going to be? So if we look here, 21.06, 0.0001, and 0.0006, if we add those up, there's some rounding happening that's changing it a little bit, but that's essentially what this multiple R squared is, that just the total. If we think in terms of Bill's Venn diagrams, and that multiple R squared is simply all of A, B, and C, all of those areas, all of that portion of the outcome of doctor's visits that is explained by all of this. It explains it covers up, about 21% of that circle of time doctors. But physical health symptoms sucks up basically all of that variance, and because it, is 21% of that, and then you can see that esteem and control have very, very, very little things. So this delta R squared, the reason that it's called delta means change, so the change in R squared. Well, what do you mean the change in R squared? Well, if we do our model comparisons here, where we talked about these model comparisons are simply saying, well, for this one, for this F, where F equals 0.066, if we compare an augmented model with all 4 of these parameters against a model that takes out this focal parameter of esteem, what does that affect? Well, it increases, it changes R squared. It increases R squared by 0.0001 to put this parameter in there. This F test for F equals 0.313. This delta R squared, that means that, how much is error reduced when we include this additional parameter? Well, we explain 0.0006% more. Well, rather not percent more. I guess that would be 0.006% more. But either way, R squared goes up by only 0.0006 when we compare including this focal parameter of control C or not. So this delta R squared, the change in R squared, this is telling you for each of these predictors how much does the explained variance increase when you include each of these additional parameters. And that's why total between each of these additional parameters, it only increases your R squared by 0.0007, which is why we don't get a significant effect when we look at that model comparison of comparing model 1 to model 2, and it says, nope, it's not a significant reduction in error. Well, that's because these other 2 parameters have tiny effect sizes. They have basically no effect on the number of times that people go see the doctor. Last thing that we'll talk about real briefly is collinearity. So as a reminder, collinearity is redundancy in your predictors. It's when you have predictors that are related to one another. And so that causes your parameter estimates to be artificially inflated. If you'd like, I can try to explain more in drill on Thursday or Friday why that's the case. But what you really need to know is that when you have 2 predictors that are related to one another, and if you regress some outcome on both of those, it will artificially inflate your parameter estimates. So the variance inflation factor, or VIF, is a measure of that inflation that is caused by collinearity in your variables. So if you compute a variance inflation factor, VIF, a VIF is bounded by 1 and infinity. So the closer that you get to 1, the better off you are, because if it's exactly 1, then that means that there is no inflation of your estimates due to collinearity. As that number gets bigger, that means that your parameter estimates are more and more inflated or biased because of collinearity between your variables. And so, if your VIF is getting up to be 10 or more, then you have cause for concern about multicollinearity. But as long as it's close to 1, then you're not concerned. So here we check and see, and sure enough, like they're all about 1, which means that we don't really have any problems. Now, to make sure that I speak to this in the terms that Bill was using, what he talked about in his Venn diagrams is that the tolerance is the unexplained portion of your, if you regress x2 on x1, then that unexplained portion of x2 will be the tolerance. So I believe if he talked, well, I could just pull this up real quick. Screenshot of this just to try to make this a little more concrete. So Bill was talking about this in lecture. So tolerance is, basically if you look at x1 here and all of the variance of x1, areas B and D are, overlapping with x2, and so like x2 explains that portion of x1, but A and F is the unexplained portion of x1. So the ratio of what is unexplained of x1 to all of x1 is that tolerance. And VIF is the reciprocal of tolerance. So what that means is, like, you can imagine that if the more, if we were to take this x2 and push it over to the side to make them overlap more, you can see how that would make your A and F get smaller and B and D would get bigger, which would mean if your numerator up here, if A and F is getting smaller, then that means that your tolerance is going down as there is more overlap, which is why you want high tolerance. If you imagine, as Bill talked about, I believe last week, that one of the great things about being an experimental psychologist is you get to have no overlap between your variables if you experimentally manipulate them. So you can imagine that if we completely separated x2 from x1 here, that there would be no regions B and D, and it's all A and F, which means, tolerance would be A plus F would be 1, and A plus B plus G plus F, sorry, that was where he scratched that out, and that should be B and D, so that's D. But basically all of it would be 1 over 1, or tolerance would be 1. And as there's more overlap, that tolerance is going to go down, and low tolerance is bad. On the flip side of that, when you take the reciprocal, the minimum is 1. And so if your tolerance is 1, which tolerance would be 1 when there is complete separation between your predictors, there is no redundancy, there is no overlap. And so if your tolerance is 1, then VIF, that variance inflation factor, will be 1 over 1, which is 1. So if there is no overlap between your predictors, your VIF will equal 1. Then as they overlap more and more and more, that VIF is going to continue to get bigger and bigger and bigger. Once it's big enough that VIF is a factor of 10, then you have concerns. But anyway, I hope that helps kind of clear up what this is actually measuring. That, again, if you just imagine that this A and F portion is the unexplained part, and you want to know how much of x1, what portion of it is unexplained. If there's no overlap, then that is the entirety. x2 does not explain any of x1. So your tolerance will be 1, because it will be A plus F divided by, there is no B and D anymore, so it would just be A plus F divided by A plus F, so 1. And VIF is 1 over tolerance. 1 divided by 1 is 1. So hopefully that helps make that a little bit clearer, and sorry for kind of jumping around today. It's been a week. Anyway, if you have any questions, just let me know, as always, and like I said, we can talk about these things in more depth on Thursday and Friday.